This webinar is being recorded and will be available for viewing later on the EAB University page of the www.emerald-borer.info website. Thank you everyone for attending today. And Sandy, please unmute your mic and begin your presentation.
Thanks, Robin. Well, this is really fun and great. And I think it's kind of interesting that I think the EAB University was something that kind of was going already before the COVID pandemic hit. And so I think that you guys were very much ahead of your time in organizing these kind of remote presentations. So I think it's pretty cool. Let's see. So thanks to you and all the whole organizers, the EA University. And I think my talk is going to be slightly different than many of the other talks that are done at EAB University, in that I'm not going to be talking about any specific pest system, but rather talking about the problem of managing invasions in general. So I hope it's interesting for everybody. I'm going to, I think that for many of us, we have experienced, those of us that deal with forest insects and diseases, over the last few decades, we've just seen kind of this steady arrival and discovery of new non-native insects and diseases, many of them quite damaging. And I think it's kind of a logical question that comes up is, well, can't we do something to stop this? To stop, to have this plethora of new species arriving. And that's really what I'm going to be talking about is the field of biosecurity. And I wanted to point out that the problem of this accumulation of new non-native species, it's not something that we're just experiencing in North America, but this is something that's going on all over the world, and it's really something that's been going on since for over almost 150 years. So the word biosecurity, unfortunately, here in the US, the word biosecurity isn't used so much for this purpose, but in the rest of the world, the term biosecurity refers to basically the process of managing invasions. In other words, preventing new invasions and managing those invasions. It's something that is of increasing importance, and in different parts of the world, it probably takes on lesser or greater importance depending on the extent to which the biological invasion problem is severe. But it's something that's really every country around the world is doing this. To really understand the invasion, the whole our approaches that we take for managing invasions, I think it's really important to kind of quickly run through the whole process, the invasion process. And this is just quickly that typically we think of their borders. Countries have borders, right? And on the other side of the borders, there are pools of potential non-native species, and those non-native species are usually accidentally transported, and we have the arrival phase, and then following the initial arrival, some of those species may establish, others go extinct, and those that do establish eventually will spread and expand into their potential range. So the other thing that corresponds to this is the different types of biosecurity activities. And typically we classify biosecurity activities into pre-border activities, that is obviously things that take place in other, don't take place before the species arrive. And then there are activities referred to as border biosecurity, which are, as this name would suggest, these are the activities that take place at the border to prevent new arrivals. And then there are finally the post-border biosecurity, which are the activities to prevent the arrival, the establishment and spread of species. And just digging into this a little deeper, for each of these phases of the invasion, we can break down their different types of biosecurity activities that focus on different phases of these invasions. And I'm going to be talking about each of these over the rest of my talk, but just briefly for before invasions happen, a lot of important things, activities such as risk analysis, quarantines, bans, phytosanitary treatments for preventing arrival there at the border biosecurity activities such as inspection, phytosanitary treatments, and then following that to prevent establishment, we use surveillance and eradication. And then finally, to prevent or minimize spread, we use barrier zones and domestic quarantines. But before digging too deep into this, I wanted to I think it might be useful to kind of review some of the myths that unfortunately surround the management of invasions that, I think that a lot of us are highly motivated. We see the damage around us and we think, gosh, couldn't we be doing more? And I think one of the myths that I hear occasionally is people sometimes will say, well, nothing that's being done that governments are doing is effective at preventing invasions. We just have more and more of them and nothing is working. And that's really not true. I'm going to be talking a little bit more about this, but this is from data from a paper that I recently published that shows on the top graph, it shows that numbers of in the imports of plants, which is one of the main pathways for pest invasions over time. And then on the lower graph shows the number of establishments of non-native Hemiptera. These are, very damaging part of a portion of the insect order. And one of the things you can see is even though there's been this pretty substantial increase in imports over the last 5 or 10 decades, we really haven't seen this a parallel increase in number of invasions. And one of the main reasons for that is that starting somewhere in the 1910, 1920 in the US and rest of North America, we started implementing biosecurity measures to try to keep these species out. And while we haven't been successful in keeping all these species out, there has been a tremendous success. And I think what very often we forget that and think, oh, nothing's working. But actually, if we weren't doing the biosecurity measures we currently implement, things would be a lot worse, I think. Another myth that I think is widely, I hear also occasionally, is people say, well, what we really should be doing is just more inspection, because that's, we don't inspect enough of the imports that come into North America, and we could be doing so much more, and that's how we could prevent all these invasions. And inspection is a worthwhile endeavor. I think, there's no question, and I could be talking about it later, that it forms a really important part of any nation's biosecurity program. But it actually, in most cases, it actually is not really an effective measure of keeping stuff out, because the reason it's easy to understand that when you think of the huge volume of imports that come into the US and other countries, it's really not practical to inspect most of it. And the stuff that does get inspected, a lot of these insects and pathogens, they're so small and inconspicuous, you really can't find them. And so inspection really is valuable more for the information that it provides, that is information about what species are coming in on what pathways. But it doesn't, in most cases, it doesn't actually itself prevent new invasions. And then another third myth that I think I hear widely too is people say, well, we should just be banned. There should be more bans, sort of indiscriminate bans we should basically just prevent imports. And if we just stopped all this importing, then, the whole problem would go away. And while it is to a certain extent true that if we stopped all imports and all international travel, that probably would greatly reduce the number of new invasions. But that really is not a realistic scenario, because the current world as we know it, we've had tremendous economic prosperity that's come from international trade, and to say, well, we're just going to stop that, it's really a little bit naive and not at all realistic. And I'll say more about that too later. And finally, the fourth sort of myth that I think I hear sometimes when people are talking about invasions, is they say, well, eradication is basically impossible. You can't eradicate a species because you can never kill every last one. And it is true that eradication is not necessarily the easiest thing in the world, but in the last 100 years, there's been a tremendous scientific advances, and eradication is increasingly successful and is actually an important tool in our sort of toolbox of tools available for us for biosecurity. And again, I'll be talking about this a little bit more. So finally, before I get into all the nitty gritty, I just want to say again a little bit of background about the history of invasions. And one of the things, as you can see, this is the number of non-native insect species. We have somewhere around 3,500 non-native insect species that we think are established in really Northern America, which is Canada and the United States, conterminous United States. And so it's, in a way, this is maybe not something that we can necessarily be proud of, and it is a little bit scary because on average, about 25 species, new insect species established every year. So this is a serious problem that continues. And the other thing I think that's important to understand about invasions is, there are many different pathways by which non-native insects and pathogens invade. But one of the most important, historically, one of the most important pathways is live plants. And these are either imported commercially or they're brought in by passengers on airplanes. But plants are sort of an ideal pathway for, if you wanted to introduce an insect or a plant pathogen, it's kind of the ideal mechanism, because when an insect hitchhikes on a live plant, that on its host, it has something to eat during the trip, and when it arrives in the non-native habitat, it has something to eat that helps it establish. So this is something that that the importance of live plants as a pathway for invasions, and in general, the sort of dangers of invasions of plant pests, isn't something that people really completely were switched on and did not recognize until the late 1800s. And in fact, in the latter part of the 1800s, there was actually a big wave of insect invasions of some pretty important serious pests that really happened because people had no idea that importing live plants was so dangerous. And so this photo shows some orchard trees that were imported from Europe and Asia. And there are many stories of serious pests that were introduced this way. One of these is most likely the hemlock woolly adelgid, which, the reality is for most of our important plant pests, we don't really know for sure how they establish. But in the case of the hemlock woolly adelgid, we have at least one scenario, which I think is the most likely, which is in a wealthy individual's garden in Richmond, Virginia. The individual wanted to have a Japanese garden, and so they hired a Japanese gardener, and they imported trees, in this case hemlocks, from Japan, and most likely those hemlocks were contaminated with hemlock woolly adelgid, and that's where, several decades later, nobody noticed it until several decades later when the first populations, the hemlock woolly adelgid, showed up in this person's garden. And so, but again, people just didn't realize how dangerous this process of importing plants really was. And it really wasn't until sometime around 1900, the late 1800s, early 1900s, a group of entomologists and plant pathologists first started to recognize the danger of importing plants. And in this case, Charles Marlett, who is an entomologist with the USDA, was one of the key people who recognized this danger. And he tried to work with the US Congress to pass some sort of legislation to try to stop this, or at least minimize this problem by regulating plant imports. There was, interestingly, there was actually quite a bit of pushback from the nursery industry at the time. But eventually, in 1912, Congress passed the Plant Quarantine Act, and this is really the beginnings of biosecurity as we know it in the United States. One of the things that the passage of the Plant Quarantine Act resulted in was actually a huge drop in the imports of commercial imports of live plants. And of course, this had by reducing the number of live plants, this had a positive effect on reducing the invasions of plant pests. But at the same time, that didn't really last forever. And after following World War II, there were increases in numbers of plant imports, but to a certain extent, following World War II is when biosecurity, as we now know it, kind of modernized, and those imports are not probably now as dangerous as they were prior to 1900. Let's see. Oh yeah, so one of the key chapters in the history of biosecurity was really the free trade movement, which happened following World War II. That after World War II, a lot of the kind of most noted economists in the world recognized that one of the causes of world wars is global inequality, and there was a recognition that free trade would promote global economic equality, and free trade would promote global prosperity. And so there was this Bretton Woods conference where a lot of this was discussed by economists, and this eventually led to the GATT agreement, which was really an international treaty that regulated the imposition of tariffs by countries. And then this was eventually followed by a series of other conventions. And finally, in 1995, there was the SPS Agreement, which, among other things, it formed the World Trade Organization. And when the World Trade Organization was formed, it recognized the International Plant Protection Convention as the governing body that would regulate biosecurity and plant quarantine. And this is one of the key things, is that historically, plant quarantines on plant imports had historically been used as unfair barriers to free trade. That sometimes countries would say, oh, there's this pest in your country, so we're not going to import anything from your country, but we'll export our stuff. And so this was considered a barrier to fair trade. And there are a lot of examples of this. And so one of the things when the passage of the SPS Agreement was that that any country could not impose a barrier unless they actually could document scientifically the existence of a specific risk that had to be mitigated by some kinds of bans or quarantines. And the SPS Agreement eventually set up what's known as the appellate body of the World Trade Organization, which is basically an international court that hears these cases on where one country is accusing another country of unfair trade practices, and they settle cases, determine whether, in the cases of plant quarantine issues, they arbitrate whether a country has actually followed the specifications of the SPS Agreement and actually can demonstrate that the risk of plant pest invasions is realistic. So when, this gets back to this question about, well, if we just stop we impose more bans on imports of agricultural products, and there would be no problems. And again, it's really not a realistic approach. And because these international treaties don't allow these kind of indiscriminate bans. You have to be able to show specific risks in order to implement those kinds of bans. Let's see. So this gets back, yeah, to maybe this question, this first sort of stage in the biosecurity measures that countries implement, and that's risk analysis. Risk analysis is used to identify these specific risks posed by that might be associated with certain types of imports, and identify. One of the things that's done as part of this risk analysis is identifying what pests are potentially associated with a given commodity that might be imported. And then obviously the probability that those pests might be transported, the probability those pests might establish, and the probability that those pests might cause damage. And this is obviously not an easy thing to do. And in fact, but it's something where there continue to be scientific advances made in making these kind of predictions, because the problem is very often there are also a lot of pests that turn out to be problematic that nobody actually had recognized prior to those pests invading. But there has been a lot of progress on this. And here in the United States, just as an example, of these kinds of quarantines or bans, for many years we've had quarantines or bans that basically prevent the imports of any kind of like live fruits or vegetables that so for most for example, most orchard tree species can only be imported as seeds or as tissue culture because of the recognized danger of importing the actual live plants. And this has been the case for several decades. More recently, about 15 years ago, the USDA implemented a program called NAPRA, which stands for Not Authorized Pending Risk Analysis. And it's a little bit different than these kind of permanent bans. And it basically is, it at least temporarily prohibits the imports of certain plant genera based on the potential damage that could occur associated with specific pest species. So just an example of this is for the Asian longhorn beetle, Anoplophora. Oh no, this is actually for the citrus longhorn beetle, Anoplophora chinensis. They're here shown about 75 genera of tree species that are prohibited for imports. And this is the case actually for most North American tree genera. It is not allowed to import these tree genera anymore, and because of the USDA recognizes the risk associated with these imports. So moving on in this biosecurity continuum, we have what we refer to as border biosecurity, which these are basically activities to prevent arrival of new pests. But these are carried out typically at the border. And this includes inspection, phytosanitary treatments, post-entry quarantine. And so we can talk a little bit about phytosanitary treatments. Phytosanitary treatments basically refer to any type of treatment of an imported commodity to reduce the risk of insect and disease contamination. And a good example of this is what's happened with solid wood packing material. And this is, again, after World War II, there was the innovation of containerized cargo. And one of the things that kind of came along with containerized cargo was the expanded use of wood packaging material and things like pallets. And in the late 2000s, it was recognized, well, a lot of times these pallets and other wood packaging materials is contaminated with insects and diseases. And the International Plant Protection Convention recognized this was a potential hazard to not only, basically to every country in the world. And so they, and some countries were already implementing their own phytosanitary treatment requirements. And so they introduced what we refer to as ISPM 15, International Standards for Phytosanitary Measures number 15, which is basically what we call harmonized phytosanitary treatments. Basically means that every country has to follow this process of either heat treatment or methyl bromide fumigation. And there have been a couple of studies that have been done since ISPM 15, which was implemented around 2005, 2010. And it shows that it isn't 100% effective, but it definitely does reduce the rate of contamination of solid wood packaging material. And the benefit there, there are other studies have been done to show that there are actually pretty significant economic benefits that come from these this harmonized standard for wood packaging treatments. Let's see, this is, yeah, getting, I think I mentioned before, inspection, again, is another really key part of border biosecurity and for preventing initial pest arrivals. But again, there's a misconception that it doesn't, in most cases, I mean, there are a few exceptions to this, but in most cases, it just isn't practical to use inspection to actually keep anything out. But it does provide really crucial information about what organisms are in various invasion pathways. And this really feeds back to quarantine activities. So, for example, if a given country recognizes that the imports from another part of the world is contaminated with some, frequently contaminated with some sort of potential pest, then that can be the basis for that country imposing a quarantine or ban on those imports. Inspection really plays a crucial role, not necessarily in the role that we often think of it playing. But yeah, it does not really function to directly eliminate pests, but indirectly it does. Yeah, I guess I'm just showing this slide. This is actually a study we did a few years ago showing that there is really pretty strong relationship between the rate at which insect species are picked up during port inspections. This is showing the relationship for scolytines, for the true bark beetles, that species that are picked up during inspections over time eventually tend to establish more than species that are rarely intercepted. And again, this is why inspection is really, data from inspection is key piece of information in identifying what sorts of quarantines or bans need to be imposed on imports. And this can include, this information is also crucial for identifying whether phytosanitary treatments are necessary as well. Another type of border biosecurity that we tend to care about less is post-entry quarantine. And this is a practice, actually it's done with both plant imports and animal imports. The idea is that rather than allowing plants to be directly imported and go out in the field and be sold, the idea is to bring them in, allow them to be imported, but they have to go into a quarantine facility where they might be placed under observation for some period of 1 or 2 years to determine if they have any kinds of insects and diseases associated with them. And there are actually quite a few examples that show that post-entry quarantine can actually be a pretty effective mechanism for screening imports. And the good thing is that it's a way that genetic material can be used from other countries can be brought in, but greatly reducing the chance of pest imports at the same time. The next thing I wanted to talk about was surveillance and eradication, which is our kind of primary tools for preventing establishment of pests after they arrive. And just to review, establishment refers to the growth of populations to a point where they no longer will go extinct. And so the important thing is, though, before we can eradicate an invading species, we have to find it first. And so the idea with we use surveillance to find these new invasions. And so the idea is we have this continual arrival and establishment of these nascent populations. And over time, those populations, when they arrive, they're very low density populations, and over time they grow. Surveillance, it can be done via many different ways. With a lot of insects, there might be methods using traps that it can be used to detect species. And the idea is, but if you deploy, a network of traps or other surveillance methods over the landscape, essentially sometimes those surveillance points will overlap with where you have an invading population and you detect that population so it can then be eradicated. But obviously, the design of a surveillance system, it depends on a lot of things, and obviously large invading colonies that are large have a higher probability of being detected. When you have more traps out there, you have a higher probability of detecting populations, and when you have a highly sensitive trap, you have a higher probability of detecting an invading population and surveillance. And so the typical strategy that's used in a kind of classic approach to surveillance and eradication is you have this kind of base grid of surveillance using traps or other methods that are used to detect these newly formed isolated colonies. Once they're detected, typically there's some sort of delimitation that's done that may be done with again, maybe using traps or other methods to delimit the spatial extent of the population. And then finally, it's treated in an eradication program. And then following treatment, more surveillance is done to confirm eradication or identify whether there are residual populations that need to be treated. And so again, so surveillance and eradication, they kind of go hand in hand. You can't eradicate anything until you have found it. And in many cases, there's no point in doing surveillance if you don't think you're going to be able, if you're going to eradicate them. But there is, interestingly, always kind of this balance between how much effort you put into surveillance and how much you put into eradication. If we put a lot of money into surveillance, we're going to find populations that are very small, and eradication costs will be less. Conversely, if we spend less money on surveillance, then we'll have to spend more on eradication because we'll be eradicating large populations. And this is something that my colleague Becky Panchin-Neal and I and others have looked at. And in the case of Liebhold dispar, we kind of modeled this where we have a really good handle on the cost of surveillance, the effectiveness, and the costs associated with eradication. We can identify essentially optimal densities of traps where you have this optimal balance between detecting populations when they're small enough that they're not so difficult to eradicate, but you also at the same time minimize the amount of money you have to spend on surveillance. And again, because surveillance, the probability of detecting a population depends on a lot of things. The sort of optimal density of surveillance or optimal surveillance effort or trap density, it's going to depend on several things, one of which is simply obviously the establishment rate. That if, in the case of Liebhold dispar, we know that we tend to have more incursions near urban centers, and so it makes a lot of sense to put a higher density of traps in these urban areas. In addition, it's a lot less expensive to put traps out in urban areas because there are more roads. It's more costly to put traps in more remote areas. And so those two things together will drive higher optimal trapping density in urban areas. And of course, the other thing I have to mention here is that not every insect or disease is comparable to Liebhold dispar. That one of the things with Liebhold dispar, we have these very highly effective and inexpensive pheromone traps. In other insects like emerald ash borer, the surveillance mechanisms are much less sensitive. And so typically, I think the experience has been with emerald ash borer has been that when populations are discovered in a given area, people realize they've actually been there for many years because the low sensitivity of detection methods. And so as a consequence, these kind of surveillance or eradication programs tend to be less effective. And in many of these cases, these kind of insects, it probably is even more important to put a bigger emphasis on preventing the species from arriving in the first place. So you can't talk about, when talking about surveillance and eradication, we have to talk about eradication. And this is one of those things where I think the word eradication itself is very scary. I've noticed that a lot of heavy metal groups actually use this word in their like albums and this kind of thing. And so I think it's a very scary word because we're talking about total elimination of the a species, the total extinction of a species. And many people question whether this is really, whether it's possible. And we've actually learned a lot about eradication from some of the work that's done on management of endangered species. That we know endangered species, we're always worried about species going extinct. One of the things we know is extinction can be promoted by what we call stochasticity, or just random changes, say in weather and that sort of thing. But also low density populations tend to go extinct because of what we refer to as allele effects. And allele effects, it's a slightly complicated thing, but it's, I think, quite important to understand how we can achieve eradication. So this is a graph showing the change in population density as a function of initial population size. And many of us are familiar with the concept of density-dependent regulation around high densities, that around high densities there might be a stable equilibrium, so that when populations are very high, the populations will decrease. When populations are low, the populations may increase, and this creates this regulation about stable equilibrium. But one of the things we've learned now is that many species at very low densities, there might be an unstable equilibrium we call an allele threshold. And there's this type of inverse density dependence, such that at low density populations, when they're below an allele threshold, those populations will just tend to decrease towards extinction. And this is something that, again, for conservation biology, people are concerned about it because we don't want populations to go extinct. But in the case of eradication, we do want populations to go extinct. And so if these unstable equilibrium, these allele thresholds, if they do exist, they can really be helpful, because we can drive populations to extinctions only by, if we reduce populations below this allele threshold, they'll just go extinct on their own, and we don't have to do anything more. And there can be a lot of causes of allele effects, biological causes. One of the common mechanisms is mate finding, but in other things like cooperative feeding or predator satiation. Cooperative feeding example would be bark beetles tend to sort of gang up on a tree, just like a pack of dogs gangs up on antelopes to kill them. That bark beetles essentially sort of tree killing bark beetles gang up on a tree to kill it. And both of these kind of mechanisms, the common thing is they create this sort of inverse density dependence, such that population growth might be higher at slightly higher population densities. But mating for sexually reproducing organisms, mate location failure is a pretty common source of allele dynamics. At low population densities, males and females simply have a hard time finding each other. And something that invading populations very often are ill-equipped to be able to handle. And so I think of it as sort of a weak link in the invasion biology of a lot of invading species. And so all this biology, it gives us some sort of scientific basis for how we achieve eradication. Application of pesticides like Bacillus thuringiensis, we can achieve eradication by, the idea is by reducing populations below this allele threshold. We simply, kill a fraction of the populations such that the population falls below the allele threshold and it goes extinct on its own. And we don't have to kill every last organism. Another approach making use of these allele effects is the use of something like mating disruption for organisms that, again, where there's a allele effect due to mate finding failure, that we basically can make mate finding even more difficult for organisms by applying these mating disruption treatments. And essentially we're intensifying this allele effect, and that facilitates eradication. So this gets back to this idea that, eradication is not possible. And we've actually learned a lot about how to eradicate species. And in fact, it is actually possible in a lot of systems to eradicate species if we detect them early enough. Obviously, when populations are established over large areas, it's much more difficult or impossible. But if you look, there's actually an interest in this, what's called the GERDA, Global Eradication Response Database, that documents historical eradications. If you look at historical eradications over the last 100 years, there's been a huge increase in the number of attempted eradications. And increasingly, insect eradications are actually successful. And again, I think this is because we've learned a lot about how to eradicate species, and that science has turned out to be very useful and effective. So the final thing I wanted to talk about is barrier zones, and how we can use barrier zones to either stop or slow the spread of species. This is something that's probably in many biosecurity programs probably receives the least attention, but it's probably something that we could probably be doing more than we currently do. And so I think it's an area for future work and improvement in biosecurity programs. And the general idea with barrier zones is basically, as the name would suggest, is just to contain the spread of organisms. This is obviously there's some of these famous examples of the rabbit-proof fence in Western Australia. But very often the goal of containment is not necessarily to stop spread, but it can also be just to slow the spread, because it can be shown from an economic standpoint, if you can just reduce the rate of spread of many organisms and essentially delay the date at which these species invade, you can actually achieve quite a bit of economic benefit in these areas that where invasion happens later. And of course, one of the kind of flagship cases of barrier zones, I think, is here in North America with Lymantria dispar, what we used to call the gypsy moth. Many of you know about this insect, and it's established all through the northeastern US and eastern Canada, and it's been slowly expanding its range. It still only occupies about a third of its potential range in eastern North America. Since somewhere around 1990, there's been a program cooperative between the US Forest Service, USDA APHIS, and state agencies to slow the spread of the gypsy moth. And essentially, the way it works is this about a 100-kilometer band around the invasion front where the spread is managed. And one of the key things about the STS program, and I think it's something that in other systems we could also capitalize on, is that when you look at the spread of invading organisms, very often it's not a sort of continuous thing, but instead we see populations that sort of jump ahead and form these isolated populations. And we know from mathematical models that this by jumping ahead and forming these isolated populations, which eventually coalesce, the spread happens much faster. And so the strategy I was going to say that usually the form, this process of sort of jumping ahead and forming these isolated colonies is something in the literature is referred to as stratified dispersal, and usually reflects the existence of two different types of dispersal: a short-range continuous dispersal and long-range stochastic dispersal. In the case of Lymantria dispar, we think the short-range continuous dispersal is the short-range dispersal of wind-borne dispersal first instar larvae. In the case of long-distance dispersal, we think it's mostly human-aided dispersal by humans accidentally moving life stages. But the strategy in the slow the spread program is the idea is to find these isolated colonies, find them using traps, and then suppress them. And by suppressing them, we can actually greatly reduce spread. And here's just based from historical trapping data for Lymantria dispar, we can actually see these isolated populations that form ahead of the invasion front. And one of the things that makes this program work so well in this insect is the fact that we have, again, this very effective surveillance tool of pheromone, in the case of pheromone traps, which are very effective and inexpensive way of finding low density populations. And in the slow spread program, again, the strategy is to find these isolated populations and suppress them. And so the strategy consists of a base trapping grid that's used to detect populations. And then once the populations are detected, to put in a delimitation grid of higher density traps, and those populations are then eventually not necessarily eradicated, but at least suppressed in this slow spread. So in a way, the strategy that's used in the slow spread program is very similar to that of an eradication program of initial fines, followed by delimitation, followed by treatment, and then followed by more trapping. And every year, there are almost 100,000 of these pheromone traps put out every year, and the whole program is very dependent on the use of handheld GPS devices and a central GIS database, which is used to where treatment recommendations are made based on the trapping data. And the program has been very effective. We've reduced the spread rate by over 50%. And so it's, I think, one of the flagship cases of a barrier zone. And this, even though the biology of the gypsy moth or Lymantria dispar is a little different than other organisms, I think in a lot of other organisms, we could be using barrier zones or could make more efforts to reduce spread than we are currently. And that's really most of what I'm going to say. I'm not really going to say much about biocontrol or other types of management, which many people consider part of biosecurity, but they're a little bit not targeted towards preventing invasion. So I'm not going to really say anything about them. So just in closing, this question, which by the way, I actually didn't come up with this title of a futile or fertile effort, but it was a great suggestion. And I think that to answer this question, I think that biosecurity is a fertile effort, that we've actually historically made great advances in preventing invasions. I think that the science behind biosecurity has really improved over the last few decades, and as that science advances, we'll continue to do a better and better job. Of course, the depressing thing is the same, we do a better and better job. At the same time, the sort of globalization, which essentially is the driver of invasions, continues to intensify. And so, we're not going to stop all invasions, but I think that we're doing better at it. And I think that the future, in the future, we'll have more tools available and probably do a better job. So that's really all I had to say. So, Robin, I can, do you want me to stop sharing my screen or just leave it?
You can leave your screen.
Okay.
That's just fine.
Scary.
People like this screen, so I guess we're good.
Okay.
Gary Lovett did comment that inspection is also, he says inspection is also our main deterrent that keeps importers complying with the regulations.
Yeah, thanks, Gary. That's actually a good point that I probably should have mentioned, that even though in most cases it doesn't actually, it's not a significant impediment to invasions. You're very right that it does have a deterrent effect, because for importers, and again, this especially varies among commodities, but when importers know that their imports could potentially be rejected, destroyed, or require additional fumigation, it does serve as an impediment to or a deterrent for importers, and probably forces them to make greater efforts to make sure that their material that they're importing is not contaminated.
Okay, we're getting some questions here. Early on in the in your talk, Ann Gilmer said, "What do you think about the Asian carp invasion of our eastern river system?"
Oh, that's an interesting question. I actually don't know, because my background is mostly with insects. I actually don't know much about Asian carp, but most of these concepts of biosecurity, they really do apply to most systems. But again, the biology is really important, because the biology of, as I mentioned before, some organisms, the concepts of surveillance and eradication work better than others. So the biology matters, but a lot of these concepts are actually very similar. That they're applied for veterinary and human health issues, in addition to plant health issues, and the same thing is true even for when you think questions about the international conventions. In addition, the World Trade Organization recognizes the even though they recognize the plant protection, International Plant Protection Convention as the responsible organization for managing plant and harmonizing plant quarantine activities. They recognize other organizations, for example, the World Health Organization, they recognize as the organization that is responsible for harmonizing global biosecurity efforts related to human health. So a lot of this are sort of parallel universes between biosecurity efforts targeting different organisms. But unfortunately, I don't know much about fish, sorry.
Okay. When and how should we shift from managing an invasion to managing an established pest?
Oh, well, that's really a good question. And I think that there's usually no good black and white answer to that. But I mean, obviously, at some point when a invading organism is widely established in a region, then obviously a lot of the options are off the table, right? I mean, obviously, after it's already established, then prevention via things like phytosanitary treatments are obviously pointless. After a species is widely established in a region, then eradication is obviously off the table, and barrier zones are even off the table. And so that's, I think, for most pests, the switch normally, things like biological control. In my opinion, biological control is a tremendously there are tremendous opportunities for using biological control for managing invasions by plant pests. This is something that really is not something that it's obviously for native species, it's not really appropriate in most cases, but there's so many examples of where biological control has been very effective when species become widely established. But obviously for a species that hasn't become widely established, then biological control is probably less important of a tool. The other thing, which I probably should have mentioned, and this is something that most of you probably know about, is that what we refer to as invasion lags. Unfortunately, there's very often a time lag between when a species actually arrives and establishes and when it's discovered. Just as examples of I mentioned before, Hemlock Woollia delegate, it probably, most likely, we don't know for sure, but it probably arrived and established in 1911, but nobody even discovered it until the 1940s. Emerald ash borer, I think we think that it probably came in maybe in the early 90s and wasn't discovered until around 2000. So these time lags are actually a big problem for a lot of these post-border activities like surveillance and eradication, because unfortunately, by the time a lot of these species are discovered, and by the time they're discovered to be potentially damaging, it's essentially too late to eradicate them. And so or even to do barrier zones in many cases. And so that's why these other management efforts like biological control are particularly important.
Okay. Ginger Nickerson asked, does forest health play a role in whether an invasive insect can become established or not, i.e. if forests are healthy, might they be more resilient to invasive insects, or is that another myth?
Well, it's an interesting question. and in fact, it's something, the question of, we refer to this as invasibility, that the question of what forests are more prone to invasion than others is something that's really an interesting question. I know it's something I'm really interested in. Even like, so for example, one of the big questions that is out there is, does plant diversity, does diversity prevent invasions? And there's some evidence to suggest that diversity prevents invasions. And then there's also evidence to the contrary, that actually plant diversity can promote invasions, because in some ways it creates more targets, more hosts for species. But it is a really interesting question of whether forest health in general promotes invasions or doesn't. I think just logically, it does kind of make sense that if you have a forest, a region where trees are generally stressed, that increased stress makes them more susceptible to a certain class of insects and diseases. And so it would kind of make sense that they might be more prone to invasions. But I would say I've never seen any kind of definite information, historical information that would document that. Maybe somebody else has some ideas, but I don't know of any good examples of that. So I think that it's a really interesting question that would be, and so like, for example, climate change, I think many of us have wondered about that in many cases, like things like drought, climate change is causing drought in a lot of parts of North America. And the question is, when you have this widespread drought and that increases stress and susceptibility of those trees to insects and disease, does that make those areas more prone to invasion? And again, it makes sense. I just don't know of any case where we've really documented that really well. Maybe the best example might be, just thinking about this, might be the what is it, the gold spotted the Agriolus in the western southwestern United States, where I think there's some suggestion that increased drought has facilitated the range expansion of that species. But although I think that's somewhat speculative still. So I think it's an interesting idea, but I think it's not fully understood how that works.
Okay. Connor Couch says, fascinating talk. Thanks, Sandy. Can you elaborate a bit upon what that final invasion stage or permanent range means? Does it mean eradication is impossible, or the organism has no additional room to spread in the invaded region?
Well, it might mean both. I mean, so the final stage would be when the organism essentially saturated its potential habitat. So if you think of North America, if there's some fraction of North America where a species could potentially reproduce because its host is there and it's climatically suitable, once it's established across that region, then we would consider it saturated and it's essentially established everywhere. So for example, I think chestnut blight is pretty close to it. I think I've heard there might be a few places in the Western United States where there actually chestnut blight hasn't gotten, but of course that's outside of the native range of chestnut and it's just in urban plantings. But yeah, I think most of us tend to agree that once a species is essentially saturated its environment, that eradication is probably impossible. I mean, there are a few cases, like I guess boll weevil, where there has been success in actually pushing back the range of a species after it was pretty widely established, but there aren't many examples of that. And another actually interesting one, I think, is brown-tail moth, the Euproctus species that was invaded around the same time as Lymantria dispar. And it actually, I don't know how many of you know the story, but of course it came in about the same time as Lymantria dispar, invaded a lot of New England, and then suddenly the range retracted, maybe because of the introduction of parasitoids. And then just in the last decade or so, it's begun to increase again. And in fact, I think in retrospect, it's a really interesting thing that when brown-tail moth had retracted to this very small area, in retrospect, we probably should have tried to eradicate it, because that was actually a golden opportunity. It had shrunk, its range had shrunk to this very small area. But I think at the time people thought, oh, it's no problem because it's in this tiny area and not causing problems. But now it's expanded its range, and in retrospect, we probably should have tried to eradicate it. But yeah.
Okay. Andrew Hughes asks, is eradication best handled on a large coordinated scale, or are there efforts by individuals that are useful?
Well, I think that that probably varies with, with plants, people do eradication, something that people do. I would say with insects and diseases, obviously eradication can only be conducted in a very coordinated way across large areas, because there's kind of no point in trying to eradicate a species in one area if you have a neighboring area where they're not doing anything and the species is going to persist. Yeah, I think by definition, it's something that has to be done in a coordinated way. And, let's face it, that is certainly a problem in many cases, because in fact, it's one of the interesting things I think about eradication from a sociological standpoint, is that most insect invasions, I think, tend to happen in more densely populated areas, because that's where people are, that's where commodities are being moved to. And so the probability of species establishing those areas are greatest. And so as a consequence, most eradication activities have to be done in urban or residential areas. And they're also very often areas where people might be the most unhappy about eradication activities. So for example, if you live in a residential area and it's being aerially sprayed with pesticides, the perception of those residents may be that they don't want that it may be, they may perceive it as unhealthy. And the other thing which is interesting about eradication is that where the eradication happens, the people that live in one area where that eradication is being carried out, they may not themselves directly benefit from that species being eradicated. That if it's say an agricultural pest, then the farmers benefit from having the eradication being carried out, whereas the residents in the urban area may feel less, they're getting less benefit from it. Although they probably do benefit, but from having less, if many of these species, if they were to establish, then there probably would be more pesticides used on the food they eat. And so, but those connections may not be immediately obvious to people. And so there are really a lot of really interesting sociological questions, I think, that surround eradication.
Okay. Daniel Gruner asks, gypsy moth seems to be a best case scenario for slow the spread, sensitive traps, females that can't fly. Is it reasonable to expect similar success rates with most other invasive insects?
Yeah, no, that's really a good point. And it's, I think, like I said before, the biology really matters. And you're very right that the Lymantria dispar is kind of a best case scenario, that we have, it's a really well understood organism. And we have a very effective surveillance tool. We have very effective treatments, and that's not the case with a lot of other organisms. Having said that, there probably are more systems where we could be doing more to slow the spread of the organisms. I mean, for one thing, even though Lymantria dispar is such a success, in part because of its biology and our experience, there are actually a lot of other Lepidoptera that are very similar to Lymantria dispar, and we probably could be applying very similar systems to barrier zone systems to those other organisms. And even other organisms, I think probably a lot of you are familiar with the SLAM project, that there is kind of pretty convincing evidence that there are measures that can be done to slow the spread of emerald ash borer. And so there probably are more opportunities for kind of coordinated barrier zone activities. And again, it's this, and in fact, the coordination is, again, is often very one of the key issues, because like eradication with barrier zones, you have to do this as a coordinated thing over large areas. And that's very often one of the challenging things.
Okay. Gary Lovett says, very nice presentation. You mentioned the economic trade-off between surveillance and eradication. Has anyone looked at the three-way trade-off between prevention, surveillance, and eradication?
Oh, that's a great question, Gary. I would say not comprehensively. There's been great, and you're probably aware of this too, that there have been studies that have, in more general ways, compared the benefits of prevention versus not prevention, in addition of surveillance versus eradication. But I'm actually not aware of any analysis that have kind of considered all of those, the optimal allocation of resources across what we call the biosecurity continuum. So again, this biosecurity continuum refers to the activities that are done, the pre-border measures, the border biosecurity, and the post-border biosecurity, like surveillance and eradication. And actually, I think that's an area of, sort of fertile area for economic analysis that does that across the continuum. So no, that's a really, really interesting question.
Okay. Elizabeth Barnes says, thank you for a really interesting talk. I often find myself trying to balance emphasizing the threat of invasive species while also trying to make it clear that there is hope. In your own research outreach work, how do you strike the balance between getting people to take the problem seriously without making them feel overwhelmed and hopeless?
Yeah, that is a good question that you obviously don't want to sort of get everyone too depressed. And I think public awareness, it's really an interesting thing. I've done a lot of work in New Zealand and Australia, and I'm always amazed at how in New Zealand and Australia, they seem to be sort of light years ahead of us in North America in terms of being sort of proactive about managing invasions. And I think that really comes down to the awareness of the public about invasions, about the sort of significance of it. Because my experience in New Zealand and Australia, if you ask just like the person on the street what they think of the biological invasion problem, they'll be able to talk for half an hour about some experience they personally have had with some invasive species and how bad it was and how what measures could be taken. Whereas I think in North America, if you ask that same question, most people will go, "Oh, well, what's that?" They're not. I think that they're not in North America. We're not as aware of about the biological invasion problem, and I think unfortunately, a lot of that just comes down to a lack of experiences that in North America we haven't been sort of burned as badly as they have in New Zealand and Australia. And to a certain extent, I think because it's those kind of public attitudes that eventually translate into national policies. But I sort of feel like in North America, we are experiencing more and more of these problems that people, ordinary people are experiencing, and it makes them more aware of the problem. On the other hand, I think the more we can do to educate people about the problem, it would be beneficial, not only in kind of promoting more forward-looking national policies, but also engaging the public in being part of biosecurity efforts, because we know that residents, just people, ordinary citizens, the sort of citizen science thing is that a lot of invasions very often are first detected by just ordinary citizens, residents, and the more we could do to, I think in the US and Canada, we could probably have better programs to kind of facilitate them. And when those programs, I think they would probably in addition to, promoting early detection, they would probably help make people more aware of the problem and be more supportive of biosecurity measures. But it's not an easy thing. And you're right, you don't want to just scare people. I think it's important to explain to people that there is stuff that can be done, but that it takes some effort.
Okay. Eric Burnett says Tennessee has a Tennessee Invasive Plant Council that provides a citizen science mapping project. Is there a citizen input project for these insect species? And also he wants you to comment on murder hornets.
Oh, yeah, I can't say for any particular state, but I do know of that there are some states have programs. I know I actually live in Pennsylvania, so I know in Pennsylvania there's a citizen science program, and there are things like iNaturalist and Bug Guide that are all systems where ordinary citizens can take photographs of insects and have experts look at them, and I think that that's definitely something where in the future there's I think it's great that people are making these platforms for promoting citizen reporting of insects. It's not an easy thing because obviously an ordinary citizen is going to be really challenged to identify what's a potentially damaging species and what's just, say, a native species or a species that doesn't really matter. But I think that there have been a lot of success stories of sort of getting participation by ordinary citizens, as well as getting participation by people like amateur entomologists to identify insects in these photographs. So I think there's a lot of potential for that sort of thing. Murder hornets in the Pacific Northwest. Again, and I'm sorry, I apologize. I'm actually not that familiar with it, but it is an interesting system where the invasion, obviously it's potentially damaging species. And I'm not that familiar with the biology of these insects, but I understand that there's some really cool stuff that APHIS in the state of Washington have been doing of capturing insects and then putting like radio transmitters on them to find their nests. So I think it's just an example of novel approaches to surveillance, that there are a lot of new technologies out there that can be utilized for more effective surveillance. But on the other hand, it's, surveillance is very often the biggest challenge. It's, again, emerald ash borer, we don't have very good surveillance options, and a lot of other species, we don't have very sensitive methods for detecting low density populations. And very often that's kind of the missing link in a lot of these post-border biosecurity programs.
Okay. Thomas Valley comments, with EAB, it seems that regulatory agencies lacked political will to diligently enforce quarantines.
Oh, yeah, well, I'm not going to dive into that one. It's, it is a difficult situation where, I think that agencies like AVIS, they have to balance the pluses in the costs and benefits, and those costs and benefits include sort of the political aspects of any program, and that's something that each agency, I think, has to do on their own. In the case of, I do think it's interesting you contrast emerald ash borer with Lymantria dispar. Again, Lymantria dispar, we do have these much more effective tools available for detecting low density populations. We don't have those with emerald ash borer. So I think that's one of the reasons why USDA APHIS was less enthusiastic about enforcing the quarantine, whereas with Lymantria dispar, it's definitely easier to enforce a quarantine because we can detect these low density populations. So it's a complicated thing, and the biology of each of these species is different, and sort of the political landscape is different for each one as well. So these aren't easy decisions to make.
Okay. Phil Marshall has a comment. Quarantine is a deterrent and an information and education tool. It acts as a stop sign by some of the public, but it also acts more like a yield sign. How do you feel about that concept?
Oh, Phil, I love your comments. You have such great insight, I think, from all your years of experience. And to be honest, I've in retrospect, I probably should have said more about domestic quarantines that, um, you know, the US and Canada were such big countries that, um, that in a way, and in fact, I think it's really interesting when you look at sort of the biology of North America, that many species in the Eastern North America are not present in Western North America and vice versa. So from a biological standpoint, it's almost like Eastern North America is a separate country from Western North America. Um, and, and, and so as a consequence, like I think what we, these domestic quarantines, which basically are things like prohibitions or requirements about movement of plant material from the east to the west or among one state or province to another, they can be really effective at preventing the initial invasions and spread of species. And again, I think Liebhold dispar is a good example. There are a lot of others. And in reality, we probably should have more plant quarantines within the United States. Sometimes I'm amazed when you look at how the systems that are used for propagating plants that I know in many Eastern conifers, they're sometimes the seeds are sprouted in the east and then they're shipped to the west and grown for a few years and then shipped back to the east. And some of those, you wonder, there are a lot of opportunities for some disasters there. But on the flip side, there is always this kind of tension between quarantine and free trade, and the free trade includes interstate commerce. That we can't completely shut down interstate commerce, and so there's always going to be a balance between imposing quarantines to limit interstate commerce, but at the same time not putting up too many barriers to interstate commerce. And I think the key aspect is always, again, going to be kind of the biological aspect of how effective those quarantines are going to be relative to the cost that they impose. And you are right, Phil, also that quarantines, they can be an educational thing, that just the existence of a quarantine, it can be something that that kind of educates important people that are in the business of moving plants and other material around. If they know that there's a quarantine, that may make them more aware of potential dangers that exist about possible contamination. So, yeah, I think domestic quarantines can be a really effective thing. But again, it can be also a hot topic where there are sensitivities as well.
Okay, I have someone else here who has said, once an invasive pest becomes established, local municipalities and landowners bear the brunt of the management costs. What are some top pest preparedness actions that city can take to be more forward-thinking and ready for these outbreaks?
Well, that's a really good question. And I think obviously, and all of us would recognize with urban areas, one of the things with urban trees that we've all learned the hard way is that diversification of tree species is probably a good way to prevent catastrophes. That we all, again, this is something I'm sure most of you are aware of already, that with so many urban areas in the eastern and western North America, that the widespread planting of elm turned out to be not such a great thing after when Dutch elm disease first arrived, and then we saw the same thing with ash. And so the lesson that we learn in all of these things is that diversification of urban plantings is a plus. I think the other thing for local municipalities is that it pays to have some sort of personnel that are devoted to agriculture and urban trees. That if you don't have people there that are in a position to coordinate eradication programs, to coordinate surveillance programs, those programs are going to be a lot less effective. And so a lot of times that's one of the things that I think and I've noticed it's one of the things that's really fascinating, that some parts of North America, they may be very well prepared. They might have really great departments of urban forestry, and then other municipalities don't have anybody. And I think that having those personnel is probably the key thing to make those areas prepared and best able to handle these problems.
All right, one more, and that's from Phil. Does diversity prevent invasion, or does it manage impact?
Yeah, thanks, Phil. Yeah, I think I sort of mentioned this before. It's a complicated thing that we know. There's kind of two sides, and probably what it is it looks like they're kind of two two processes or effects of plant diversity that have kind of opposing forces. That when you have a landscape with a greater diversity of plants, that in some ways it intensifies what we refer to as the dilution effect. That is, that when with a lot of plant feeding insects, when you have a lot of diversity of plants, then those insects might not be able to find their hosts as well, and the populations might not build up as much because there's not sort of this critical mass of their host. But on the flip side, there's what we refer to as the facilitation effect. That is, that by having greater diversity of plants, it actually creates more ecological niches for plant feeding insects. And so it actually increases the chance that an insect that is arriving in a new area might find a host that they could reproduce on. So, and it seems like those two factors seem to have opposing influences, and in some cases kind of balance each other out. And from the perspective, again, of municipalities and landowners, I think that both, it's hard to say how those processes are going to play out, but kind of the important thing is actually sort of a risk aversion that comes from diversity. That if you have all your investment in a single species, there is a greater chance that you'd be totally sort of wiped out, and that when a pest arrives, it might have a more catastrophic impact. And so from a risk aversion, there's probably benefit of diversification by just reducing the impacts. Yeah.
Okay, thank you so much, Sandy, for this presentation.